Okay, so we left off yesterday. We were talking about the sine wave. Did you guys have any questions off the homework from those? Doing pretty good? Okay, so today we want to talk about RMS. RMS stands for root mean square. It is the root or the square root of the mean. The mean is just the average. You add them up and divide by how many are there of the squared voltages. RMS voltage is the equivalent DC voltage that will dissipate the same energy, the same power through a resistor as the AC voltage. So we're talking about this waveform yesterday, the sine wave. Well, for current, the peak to peak is 170, or for AC voltage, the peak to peak is 170 volts to negative 170 volts. So it's 340 volts peak to peak. And the cycle, anybody know what the cycle length is? 1/60th. You got it. So one cycle is 1/60th of a second. We call it 120 volts because that is the RMS voltage. So I want to take a look at where that 120 comes from. Square root of 2 is the conversion. But where it actually comes from is your phase angle. You got 0. We're going to go up by 5s here. All the way up to 360. Oops, there's a little bit of a jump. I should probably stop at 355. So the voltage is equal to 170 times the sine of that angle. Well, come on now. It's got to be radian and not rad. It was doing this to us at the end of yesterday too, wasn't it? Yeah. Okay, so it gives me the sine of pi. That's not right. Okay, let's do some conversions here. I forgot an S, that's what it was. Yep, that was what it was. The converter is radians, not radian. There it goes. Okay. So what I'm doing is I'm just going from 0 to 355 degrees, which is one complete cycle going 5 degrees at a time. And I've done here is I've listed the voltage at each spot in that cycle. So at 0 degrees is at 0 volts. At 30 degrees, we're up to 85 volts. 60 degrees, 147. At 90 degrees, we're at that full peak of 170 volts. Then it comes back down. Where does it hit 0 volts again? 180. It should be back down to 0. You can see it's a little off. probably just the conversion of the radians. 10 to the negative 14th is about the same as 0. Then it goes negative. Where would it hit the negative trough, the negative 170? Another 90 degrees, right? 270. So negative 270, we're at the negative trough, the negative 170. Of course, at 360, it should be about back to 0. And you can see we're getting down back up to 0 again. If I had 360 there, it would be 0. Root mean square, the root of the mean of the square. So we actually have to go backwards on that. The first thing we have to do is the square. So we're going to do equals this number squared. So all that's going to do is it's going to make all of them positive because we're squaring them. And of course, it's going to square them. So we've got all those numbers. That's the root mean square. Sorry, that's just the square. Next, you have to do the mean. Well, the mean is just the average. You add them up and divide by, well, if I'm going by 5s here, suppose there's 72 of them. So I add all these squares up and I divide by 72. So give me a mean of 1,440, so that's the root. Get 120.208. So you can see that actually does work out to 120 volts. I don't know if that makes any sense. We say it's the root of the mean of the square, so if we do the calculation, you have to do it backwards. You square each voltage first, find the mean, then do the root of that mean. But that's where it comes from. If you average them all out, like you said, it's 120.2 volts. In practice, the magic number, the square root of 2 is actually what it comes out to be. The RMS voltage is equal to the peak voltage divided by the square root of 2. Now, 1 divided by the square root of 2 is 0.707. But if I do this, this is going to be 170 divided by the square root of 2. And there we get the same thing, the 120.208. Now, if you did the 0.707, 170 times 0.707, you get roughly the same, just slightly rounded. Because technically, not really, no. Because we're going to call it 120 volts either way. Current is going to be the same thing. RMS current is just going to be the RMS voltage divided by whatever our total resistance is, or impedance of that circuit. Well, it comes out to be that RMS current is the peak current divided by the square root of 2. So if I tell you that we have voltage peak of 430 volts, what is our RMS voltage? Yeah, 430 divided by the square root of 2, which is 304. A common industrial voltage, by the way, the industrial voltage of 440. How would I find the peak? Well, I know that my RMS is the peak divided by the square root of 2. From solving that for the peak, I'm just going to multiply both sides by the square root of 2. So the peak voltage is going to be the square root of 2 times the RMS voltage. So it's going to be 440 times the square root of 2, or 440 times 0.70, or 1.404. What's that come out to be? Should be like 6. Yeah, you're right, 622 volts. If I ask you for, well, if I tell you that the voltage peak to peak is 680 volts, find the RMS voltage. What does peak to peak mean? Yeah, top to bottom. It's twice the peak. So yeah, peak to peak would be here. So that is saying that from here to here is only 340. So that's what you're dealing with. And yeah, that should be about 240.4 or something like that. Just 240 volts is good enough. So if I have a circuit that has, let's give it a resistance of 1.2 kilo ohms, peak voltage of 170 volts, I'm going to ask you to find the RMS current. There's two ways we can go about doing this. We can find the peak current. The peak current is going to be the peak voltage divided by that resistance. So 170 divided by 1200, right? So that is 0.1417. Now that's peak. To turn that into RMS, we take the 0.1417 or 141.7 milliamps and divide by that square root of 2 again. So you get 1 point. Well, that didn't work. 2 point. That sounds about right. Yeah, 100.2. Yeah, so 0.100 or 100 milliamps. Well, let's do it the other way. The other way we could have done that is convert our voltage to RMS first. So it's going to be the 170 divided by the square root of 2, which is 120. Then we would use that to find our RMS current. So 120 volts divided by 1200 ohms is 0.1 amps or 100 milliamps. Now in this case, it probably was easier to convert the voltage to RMS first, but it really doesn't matter. The only thing is when we use Ohm's law, that V equals IR or E equals IR, depending on how you have it, you're using it. It is either V peak equals I peak times resistance, or it is VRMS equals current RMS times resistance. Those two have to be the same. So if I tell you that the RMS current is 1.4 amps in a circuit with a resistance of 400 ohms find the peak voltage. Well, I would start out by finding peak current, 1.4 amps times the square root of 2. Just peak. Just peak. Sounds about right. So 1.4, I divided instead of multiplied. I gotta do that again. 1.4 times the square root of 2. 1.980 amps. And then, yes, I know I have to do my voltage peak is going to be that peak current times my resistance. 792 about, you got? I had 791.96, close enough. Yep. That works. So if I give you voltage peak to peak, .480 volts, resistance of 3.8 ohms, find the RMS current. No, that's 3.8, yep. Sounds about right. So our first step is to do that peak to peak voltage into just a peak voltage. So 480 divided by 2 gives us 240 volts. Then we have to convert that to RMS. So 240 volts divided by the square root of 2. So we've got an RMS of 169.7. So then the current is that voltage divided by the 3.8. So I'm getting 44.66. You multiplied? Okay. Any questions on all that? I think it's a... So just for fun, if I were to ask you to graph y equals 4 sine x, how does this vary from our standard graph? Let's look at it this way. I want you to tell me these three things. Amplitude, wavelength, and shift, phase shift. What's the amplitude here? 4. That's because of the number that multiplies in front of the sign. Nope, that's just your amplitude. You go up 1, 2, 3, 4, positive 4 here. Down 1, 2, 3, 4, negative 4 here. That's how high the wave goes. Instead of going up to 1, it goes up to 4. The wavelength here is 360. That's whatever number's in front of the x. You take 360 divided by that. That gives you that wavelength. So yes, this is going to be 1 complete cycle in 360 degrees. And the phase shift is 0. There is none. The phase shift would be a number added or subtracted to the angle out here. So We're going to start out here, 4 at 90, 0 at 180, negative 4 at 270, 0 at 360. All look familiar?
Yep. He thought we might come back, right?
Okay. How about y equals sine? Let's make this a little more easy. Yeah, what the heck? We'll leave it at that. Y equals sine of 2x. First of all, amplitude. The amplitude is 1. Because there's nothing multiplying the sine, so that's just a 1. There you go. Our wavelength is 360 divided by that number, which is 2, is 180 degrees. Phase shift, still no phase shift. Yep, that would have to be added or subtracted here. Like I said, the way to think of this number is that's the number of cycles that occur in 360 degrees. So we're only going up to positive 1 and down to negative 1 here. We have to complete a cycle in 180 degrees now. So we have to be back to 0. So the other 0 would be halfway at 90. So 1 and negative 1 are at the halfway points. Yes, that's also the frequency. There's 2 waves in 360 degrees, or in 1 cycle. Pretend those look even. A little wrinkle from yesterday. What if I throw in y equals cosine x? Not quite. Remember, this is all off that unit circle. Cosine is this length right here. So at 0 degrees, what's the value of the cosine? It's 1, right? At 0 degrees, that's a length of 1. As we get larger, that gets shorter, right? You see it? That length gets shorter. Until we hit 90 degrees, the cosine is 0. As we go this way, now it becomes a negative number. Until we hit 180 degrees, it's at negative 1. Back to 270. At 270, it's at 0. And at 360, again, it starts growing until we get to 360, it's at positive 1. So it's the same wave. It just starts at 1 instead of at 0. Compare it to a sine wave.
What would it look like if you had a graph like that?
That's exactly how it looked like.
The y equals.
The cosine x? Yeah. That blue line is the y equals cosine x.
What if you have 2 of them there? You can't graph it like that.
You think y equals cosine x and then another trig function? That gets ugly. We can do it.
Well, I mean, the homework.
So what I have here is y equals sine x. This one will be equals cosine x. We'll run them all the way down. Like that. You want to do them like plus each other? And I'm going to do the graph separately here first. This is y equals sine x. That one should look familiar. See if this works doing non-concurrent. There's y equals cosine x. So this is sine, cosine. Do sine plus cosine. It's actually kind of a neat graph. Let's get back here. Oh, no, it won't. You can see it looks like just a sine wave that's been shifted. What it does is it shifts both of them. It averages them out pretty much. Remember, if we put these, let's shrink these down so we can see them all together. Get out of there. Bring this down here. This computer? I was about 5 years old. Yeah, it's a little slow. I have avoided. I was eligible to get a new computer, I think, 3 years ago, but I didn't because they went away from having the touch screens. And so I'll be getting a new one this year because they finally went back to them. Enough people were using them that they decided they'd go back to them. What the heck? Come on now. So you can see what's happened is it shifted to the right from the cosine, and it shifted to the left from the sine. It's basically the average. The cosine has its peak at 0. The sine has its peak at 90. This one has its peak at 45. Just kind of averages them together. Now you can play with the frequencies in there, but we won't do that here. It used to be kind of tedious. But yeah, you can see that all that the cosine is the sine wave shifted over 90 degrees. If I did y equals sine of x plus 90, that would give me that red curve. That would be exactly the cosine wave for the same thing. So what if I give you y equals 2 sine of 3x? Amplitude is 2. And 3 cycles. Frequency of 3 or wavelength of 120. So I'm going to do this. 30, 60, 90, 120, 150, 180, 210, 240, 270. A complete cycle is 120. So a complete cycle will be right here. Does it start out at 0 or 1? Starts out at 0. Complete cycle there. So the half point's going to be here. So the peak's got to be the quarter wave. And the trough is going to be there. Here's the wave. So that's this one. What if I give you y equals cosine of 2x. Well, the amplitude is going to be 3. What is the wavelength? So 180. Very good. 2 cycles, 180. So it's going to end right there. It's going to be a full cycle. But that's not going to be a 0 point, is it? This one starts at its peak, right? So the halfway point is going to be 90. The quarter point is going to be right here. It's going to get to 0 right there. At 90 is when it's going to reach its trough. The 3/4 point's right there is when it's going to hit 0 again. This is going to be back up at its peak at the end of the cycle. Does that make sense? So the period is similar to these. The period is the time, the time for one cycle or one wave. Wavelength, as we saw, we use the symbol lambda for wavelength. For period, they use the symbol T, capital T. That is the actual physical length of the wave. Usually we go from peak to next peak. But it can be any point on the wave. It can be trough to trough. It can be 0 to the corresponding 0. Got to be careful with the zeros. Like here, if I start at 0 here, the corresponding 0 is not until over here. This 0 is not a corresponding one because the wave's going down there. It has to be in, both zeros are increasing points on the wave. Frequency. So we use the symbol F for frequency. Is the number of waves. Number of cycles. Well, technically it's per second. Not necessarily. That's how you guys did it, is 360 degrees is equal to 1 second? And that's what I've been saying, is 360 is a single second, so the frequency was the number of waves in 360. But in reality, it's not necessarily so. Technically, 360 degrees is usually a 60th of a second. If you're looking at your standard wavelength coming out of the wall. Yeah, it's all on how you interpret it. The relationship between these, of course, is your frequency is the reciprocal of your period. 1 divided by your period. So if you know your frequency, what's the standard frequency? It's usually megahertz, right? Gigahertz? Okay. Let's use your 2.4 gigahertz then. So that is 2 trillion hertz, right? Yep, it's like that. 2 trillion hertz. Which means the period is 1 over that. Or I think of it like this. I put this over 1. I can cross multiply 1 times 1 divided by the 2.4 gigahertz. Now I'm just going to do this. 1 divided by 2.4 gives me 0.4166. 0.4167. giga, the reciprocal of giga is nano. So that's 0.4 nanoseconds is what that period is. Or 416.7 picoseconds, if I wanted to go one more notch. Did you guys get into nanoseconds and picoseconds, or just guys hit milli and micro? Nano, that's 4. Nano is 10 to the negative 9. Pico is 10 to the negative 12, yes. Okay, so these are your velocity of your wave. Just remember what this expression is? It's your wavelength times your frequency. Well, you guys don't necessarily know your wavelength, but you know your velocity is speed of light. Because you're getting on fiber, you're sending a light pulse, right? Your speed of light. No. Electricity will go slower. But speed of light is 300,000 kilometers per second, or 300 million meters per second, equals our wavelength times our 2,400,000,000,000. Now what I'm going to do is this. I'm going to cross off 6 zeros. So this is 300 divided by 2,400. Gives us a wavelength 0.125 meters. So at that frequency, that 2.4 gigahertz, you're getting a 0.125 meter, or 12.5 centimeter wave. What's that? Yep, because I'm dividing off, I just divided both sides by 1,000,000. And then 300 divided by 2,400 is 3 divided by 24, or 1 divided by 8. Remember I mentioned math's about patterns? You get good at recognizing the patterns, the calculations look simple. So that's our wavelength. Either, like I said, 0.125 meters or 12.5 centimeters. I think we're going to call it a day there. Next time we meet, we're going to talk about angular velocity, which is going to require these linear velocities. So we'll come back and talk more about these for now. I'm going to give you a homework assignment, which should be out of that same packet. I'll have you guys double check and make sure. Page 367, I think, is in that packet. 1 through 25, the odd. And I am going to send a quiz with you. I think you got that packet.
Yeah, you gave it to me earlier. Altering currents one?
Yep.
Yeah. So none of us just remind none of us had to hear one today.
Yep.